So for today's class we will be looking into some more BJT configurations, some more circuits where we are using the BJT within the circuit. And last days we saw the common emitter, common base and common collector configurations. We will see some more configurations in this class. So let us start. I will share the content. So here you can see the first one is the fixed bias configuration, and you will find that this is the same as the base bias basically, and there is a very small difference. The difference is here that in the base bias there was a VBB and a VCC tied separately to the base and the collector circuits, collector sides. Here the same voltage source VCC is connected to both the base and the collector. Now this doesn't change the functioning of the circuit as such. Okay, right now you are seeing these two capacitances, just ignore them for some time. I will tell you what they are supposed to mean. So first just look into this part. So we have tied these two resistors to the same voltage source. So you will often see that this type of arrangement is done, but this does not change any functionality of the circuit with respect to the previous base bias that we had discussed. So the common emitter or the base bias configuration, this is also known as the fixed bias configuration. Why it does not change anything? Because what we actually need, we need some voltage, we need some current here in the base circuit that is driving the gate, and we need a current in the collector circuit which will produce a voltage drop VC. So if you remember, we basically calculate the IB and the VC. So to calculate the IB and the VCE, we don't need to connect two separate voltage sources, VBB and VCC. We can use the same voltage source because we can play with the resistances. If we want to change the IB, we can simply change the RB. It will change the IB. If we want to change the VC, we can play with the RC. It will change the VC. So we have these two resistances to play with, to tune, and that can actually tune your Q point, operating point. So in many configurations you will see things like that, things like this, that the same only one source voltage is there, only one DC biasing voltage is there, which is the VCC. Now what about these capacitances? So basically what happens, or what you will see coming forward in the course, that these transistors are normally used to amplify. There is a specific operation known as amplification by these transistors, where we are amplifying an AC input signal. We are amplifying an AC input signal. So we have some AC input signal, as you can see here, and we get some AC output signal from this circuit. Okay, so for when we have this AC signals in the circuit, we use these capacitances in the circuit also, along with the resistances. We also use the capacitances in the circuit. So this makes the total configuration. So previously we were only looking into circuits where we had resistors, but from now onwards we will look into circuits which have resistances as well as capacitances. However, the interesting thing is this, that when we are solving the circuit, we will solve separately for DC and separately for AC. So one part of the entire course is the DC biasing configurations. So right now we are dealing with DC biasing configurations. So we are trying to understand what is the DC operating point, or what is the Q point The Q point is a DC voltage and current level, VCEQ, ICQ, that is the DC operating point. Okay, so in that level of current and voltage the transistor is operating, but that is a DC level. On top of the DC there would be an AC signal coming in. There we would, that part of the course is known as AC biasing configuration or AC biasing analysis or AC analysis of BJT. Now we are talking about DC analysis of BJT. Both these two can be taken, both these two are taken separately, but they form the same problem, because in a particular problem or in a particular circuit, what we are trying to do, we are trying to amplify an AC signal on top of a DC level. So there is a DC level in the circuit, on top of that we are trying to amplify an AC signal. So that is the totality of the operation. However, that total operation can be very easily separated out into the AC component and the DC component. And when we separate it out like that, then we have to first get the DC biasing circuit from this total circuit. So in the total circuit you will find these capacitances, but in the DC biasing circuit you will see that these capacitances are opened. The capacitances are open circuited. You see, this capacitance no longer is present here, it is open circuit here. This capacitance, which is the output capacitance, is open circuit here. Why we have been able to make the capacitances open circuit when we are analyzing the DC biasing condition? Can anyone tell me that? Can anyone tell me that? No answer? There are 68 people in the class, I can see. This is very simple. Please try to remember your network analysis. You have done some AC analysis also, or haven't you? In your network theory class? Am I audible?
Yes, sir.
Yes, sir.
Yeah. So please answer. Someone answer. Is AC analysis done in your network theory classes? Working with AC circuits? Of course, I think it is done.
Yes, sir.
So you should be able to answer this question. Why we are able to make the capacitances open circuit when we are dealing with DC signals? Tell me.
Sir, capacitor acts as open switch in DC.
Why?
Open circuit. Sir, because omega becomes 0.
Right. Because omega becomes 0 and omega is in the denominator for the impedance. When we are trying to calculate the impedance offered by the capacitance, it is 1 by 2 pi fc, right? 1 by omega c. So that omega becomes 0 because the frequency is 0 in DC. So that's why we are able to make the capacitances open circuit. Okay, very simple answer, but these very simple things only make up the entirety of any electrical analysis. There are very simple electrical fundamental laws. If you remember them, if you are used to working with them, then any circuit, any problem you will be able to solve. I will not say very easily, but given some amount of effort from your side, how to work with those laws and all, you will be able to solve the circuit. Okay, so you should have confidence in your knowledge and whatever you have learned from the different courses. So now you see, now what we have to do, So the first thing, whenever we are given a circuit, when we are trying to understand the DC biasing condition or the DC analysis we are trying to do, we have to make the capacitances open circuit, and in electronic circuits normally you will not see inductances, but if there are inductances we make them short circuit. And now we are seeing at a circuit which is having only resistances in them, and then it becomes very simple. We have previously analyzed, so now we have come to this particular circuit. This is equivalent to this is the DC equivalent circuit. Should write this, sorry, it suddenly zoomed up. Okay, so this is known as the DC equivalent circuit of this particular circuit. So we are looking at the DC equivalent circuit. So in any biasing, any other biasing configuration also we will be doing this. This is the first step that we have to do. Now in the DC circuit we have to simply solve for the IB and VC. That's all that we are always doing. So it is very simple. IB is basically VCC minus VBE by RB. That's all. Then IC is beta times IB. This is from the knowledge of this is from the BJT characteristic. Like this is the BJT law. IC equals to beta times IB. Then again we are applying the KVL. VCE equals to VCC minus ICRC. We solve everything, we get everything. Okay. So now V is directly connected to the ground. So your VB is basically VB equals to VBE, and VC is also equals to VCE, since VE is connected to the ground. Okay. And the IC sat is the saturation current. The saturation current is when your VCE is 0. Then you solve for IC. So in this equation you put VC equals to 0. What you get as IC is IC sat. So this is the analysis you will do for any configuration. These are the things which you are asked to solve. Very easy things. But let us go through the different configurations, very standard configurations which are there in the book also. So I will make you go through them one by one. The next one is the emitter bias configuration. You must be remembering this name. This is the common base configuration also, right? So this is one type of common base configuration, because in the end also you will see that there is another common base configuration looking a bit different. Okay, so now this is the emitter bias configuration. Here this is the how it looks, and when you make the DC equivalent circuit, the capacitances are removed and this VCC can be separated out in these two branches. So what happens, you see that your you apply the KVL in this loop, in the input loop you apply the KVL. So you know the VCC minus IB RB minus, so here I will draw the currents which are not drawn specifically. So this is IC, this is IE, and this is IC. Sorry, this is IB. So you see this equation, the first equation, VCC minus IBRB minus VB minus IER equals to 0. Now IE and IB are having a relationship, so you convert everything to IB and then you solve for IB and you will get this equation. Now there is the now this gives rise to one important point which we have not discussed earlier. This important point is about this resistance beta plus 1 RE. So what is this? Is not a resistance. We have resistances RB, RC and RE in the circuit, but when we are calculating a current, it is some voltage divided by some resistance. Now if you look at the input side circuit, this voltage VCC minus VBE is the resulting voltage, you can say. So VCC is the supply voltage and VBE is a drop, we know. The resulting voltage in the circuit is VCC minus VBE, and in the input side a current IB is flowing. So if you only look from that side, then RB plus beta plus 1 RE appears to be the input loop's resistance, right? It appears to be the input loops or the base emitter loop's resistance seen from the input side. So IB being the input current, the IB sees a resistance of RB plus beta plus 1 RE. This IB, the input current, is seeing a resistance RB plus beta plus 1 RE, not simply RB plus RE. Okay. So this RE resistance, when it comes to the input side, so the RI, so this is called the reflected resistance. Reflected resistance is beta plus 1 times of RE. This is the important point we are coming across for the first time. Okay. So when we are seeing from the input side, the resistance connected to this emitter is multiplied by beta plus 1 times. It increases. Okay, it increases by some times, by quite a number of times, 50, 100, 150, like that. So the current sees too great a resistance. So some multiplication of this resistance RE the current sees. So this is called the reflected input resistance, and you will see this reflected resistance in other solutions of the other different configurations as well. So keep this in mind. Okay. Now let us go ahead. So this is simply solving the, what we did, we did not do much, we did only KVL here, but something we saw here peculiar, and we found out what it is, what it means conceptually, that we found out. What does beta plus 1 RE mean conceptually, and that concept we have cleared now. So it is the resistance seen by the input current IB. So it is the reflected resistance to the input side. And now when we have solved this much, then we can figure out what is VCE. So we have another equation in the output loop. So this is the output loop, and we can find what is VCE. So there is one approximation, IE almost equal to IC. And then what is IC saturation? You make VCE equals to 0, you will get IC saturation. Okay. So here you see the IC saturation is simply VCC by RC plus RE. So this resistance RE in the output side appears as it is. So the output current IC sees this resistance RE as it is. Okay. Specifically, it is, of course, there is some ratio of IC and IE. There is that alpha term was there, but that alpha is very very close to 1. So it doesn't matter so much. So the resistance RE remains same in the output side. So after talking this much, we have this voltage divider bias configuration, and this is the most this is where you will face some challenge to solve. Now I want to ask you one thing, whether you have been you have been taught the Thevenin's equivalent circuit. Can someone answer me?
Yes, sir.
Yes, sir.
Thevenin, you know.
Yes,
okay,
sir.
very good. So I don't have to explain much on that side. So here we have to employ the Thevenin's equivalent circuit. So when do we normally employ the Thevenin's equivalent circuit? So this, I think you are able to understand, is a DC equivalent circuit in this side. Now we have to find out what is the current IB. What is the current IB we have to find out. Okay. So here there is some IE, this is the IB. Now how can we find out this IB? So if we try to work with this loop, we don't really know what is the current here. So there is some current I1 flowing here, some current I2 flowing here, and this will be the IB. This is the driving current, driving base current. So if we want to analyze this loop, we are not able to do it because I2 is not known. If we try to analyze this loop, I1 is not known. So there is a lot of complication here that is appearing. So in this situation, what we do, if we want to find what is IB, we simply replace this entire input side with a Thevenin's equivalent voltage and the Thevenin's equivalent resistance. So you see this thing, I will zoom out a bit. So this thing is replaced by a ETH and a RTH. This ETH is the Thevenin's equivalent voltage and the RTH is the Thevenin's equivalent resistance, and that is driving the IB. We can assume that in that manner. So this IB is getting driven from a circuit. Obviously there is some circuit, some network here that is producing the IB, and that network can be written as an Thevenin equivalent network, ETH RTH. When we do this, then life becomes simple for us. Now this is a single loop. So if we know ETH and RTH, of course we have to find out ETH and RTH. Once we know the ETH and RTH, then this is a single loop and we can analyze it. IE and IB has a direct relationship with each other, so we can solve for IB. But first we have to calculate what is ETH and RTH. So for this network we are trying to find out ETH and RTH. So let's see how to go ahead. So when we are trying to find out ETH and RTH, this network is drawn in this manner. So try to observe the equivalency. Try to observe the equivalency between this network and this network. So here nothing has been done. This VCC is drawn in this manner with plus and minus signs, and this minus sign will go to the ground obviously. So this point is taken to the ground and the R1 comes. This R1 comes here, and from there the R2 is coming and that is grounded, and then the rest of the network is like this. So now we are trying to solve the Thevenin's equivalent of this blue shaded part. We are trying to solve the Thevenin's equivalent of this blue shaded part, and that is solved very easily. You know how to solve Thevenin's network, Thevenin's equivalent voltage and current, voltage and resistance. So when we are trying to figure out what is the equivalent resistance, what we do, we short all the voltage sources. So we short all the voltage sources and open all the current sources. So here only a voltage source is there and we short it, so it is 0, and then you see that what is the resistance seen from this side. So you see only R1 and R2 are in parallel, so that is the RTH. So RTH gets known, and then what is ETH? For ETH you have to only figure out what is the open circuit voltage. So you remove this load circuit from here, from this side, and you see what is the voltage here appearing in this part, in this between these two terminals, and that is very simply figured out. This R2 by R1 plus R2, it is the divider, voltage divider coming into picture. So this is the reason why it is called a voltage divider configuration. This R2 by R1 plus R2 VCC. Okay, so ETH is also figured out. So this is so now you know ETH and RTH, and from this particular circuit you can write your KVL and you can solve for IB with this assumption IE equals to, this is not an assumption, this is a relationship, IE equals to beta plus 1 IB. So you find out what is IB. Here also you can see that the RE is getting reflected in the input side by multiplication time beta plus 1. When you find the IB out, you can also get the VCE from the output loop, and IC is nothing but beta times IB. Okay, the circuit is solved. Now in this is the exact analysis of the voltage divider configuration. In the exact analysis there is some complication. You have to do the Thevenin's, you have to find out the Thevenin's voltage and the RTH has to be figured out. So all these different some complications are there. There is also another analysis which is the approximate analysis. In the approximate analysis, the VBE, this VBE is assumed to be 0. So when this is assumed to be 0, when this voltage is assumed to be 0, then this point and this point are the same point, this point and this point are the same point. So what is IB? This IB can now be assumed to be flowing through this resistance, but this resistance is not RE. This is the resistance seen by IB as the reflected resistance of RE. This is where the concept of reflected resistance comes into picture. This RI is not RE, it is beta plus 1 times RE. So this is the approximate analysis, and in the approximate analysis you simply have the voltage divider circuit like this, and this branch is coming out where this resistance is not RE anymore, it is RI. However, when this RI is much greater than R2, this you can set, because R1 and R2 is in your hand, so RE is also in your hand. So this you can fix in this manner, so that you can do the approximate analysis basically. So for doing the approximate analysis, you can make the circuit, you can prepare the circuit in this way that your RI becomes much greater than R2, and then you can employ the approximation here that when this resistance is much greater than this resistance, obviously most of the current will flow through R2 and very minimal current will go to RI. So IB is very small in that situation, and that is what we wish to keep also. IB we wish to keep very small as well. So in this situation, I1 and I2 can be assumed to be same, and when we assume I1 and I2 to be same, now we can very easily calculate the voltage VB. So assuming this IB becoming 0, this voltage VB is nothing but the voltage appearing in the voltage divider circuit with resistances R1 and R2, and that is R2 by R1 plus R2 VCC. So the VB we get directly, and when we get the VB, now we again look back into the circuit. So this VB we get, and since the approximation says that VBE equals to 0, so VE equals to VB. We are using the approximate analysis, so VB is equals to 0, and VB what we have got is also equals to VE. So the current IE we can get now, IE will become VE by RE. IE will become VE by RE, and VE is nothing but VB. You can also write VB approximation, but sometimes you can say that now I will introduce the VBE. You can do it, but normally in these situations, in the approximate analysis, VBE is mostly taken as 0. Okay. So now with IC almost equals to IE, then VCE you can calculate again from the output loop, and this is also IC saturation what you are finding out by making VC equals to 0. So this makes the entire analysis of the circuit voltage divider configuration. I hope there was nothing of much difficulty to understand the voltage divider configuration. You are suggested to read the book once if you have any difficulty, and that explains it with a lot more details. Actually, some finer points may also be given in the book. Anyway, we are coming to the next configuration, which is the collector feedback configuration. In the collector feedback configuration, a feedback resistance is added. Here you can see this RF. This is taken from the collector and put to the base. So there is a resistance between the collector and the base. This was previously not there. Previously the base resistance was directly coming from the source VCC, but now it is coming from the collector. So there would be some changes in operation. Okay, one thing I forgot to mention, in voltage divider you observe that your IE is not dependent on IB. This is the situation where we can say that the Q point becomes very stable. This is something we are wishing for, that the Q point becomes very stable. At least for amplifiers we have to wish this, that our Q point is stable. So we have to try to make our configuration in such a way that the Q point is stable. So in emitter bias, in fixed bias, the IC was very much dependent on IB. It was beta times IB. So it was not a very stable Q point. Emitter bias had a more stable Q point, but in the voltage divider the Q point is very stable. Okay, at least you see in the approximate analysis there is no mention of IB anywhere in the approximate analysis. It is very stable. In the collector feedback configuration also something like this happens because of this feedback. So let us see what happens. Now you please observe that the input loop is like this. So VCC, the base emitter loop or the input loop, VCC, then some current IC dashed is flowing in through RC. It is not IC, it is IC dashed, because IC is the collector current which appears after this node, So before this node it is IC dashed, after this node it is IC and IB separating out. So what is IC dashed? It is IC plus IB, that's all. So it is IC plus IB, so it is basically IE anyway, because here IE is again IC plus IB. However, we are denoting it as IC dashed in this case, as normally the books are denoting, and then the loop comes to this part where we have IB RF as a voltage drop, then we have a VBE voltage drop, and then we have a IE RE voltage drop. So you see these voltage drops appearing here. So that makes the complete KVL equation, and from here we can make the approximation that IB being very small, IC dashed is almost equals to IC, IE is also almost equal to IC, and IC is beta IB. So when we replace all these things in this equation and take IB to one side, we can calculate what is IB, and it comes out in this manner. You can do the intermediate steps for yourself. IB comes out like this. Here the interesting thing to note, there is again a resultant voltage in the input loop, and then this base resistance which is the feedback resistance now, and the RC and RE both reflected. Previously only RE was getting reflected, here RC is also getting reflected. Why? Because obviously RC is carrying IE, IE is getting carried here also. Okay, so it is getting reflected. So we can write it in this manner, V dash by RF plus beta R dashed, to do some further analysis. So now when our IB is this, IC we have to find out, the operating point is IC VCE, that is the operating point. So we have found out IB, so IC is beta times IB, so we have to use that beta times multiplication. However, even with that, this circuit becomes stable, because as you can see here, beta times IB is basically, you take this beta downside in the denominator, it becomes RF by beta plus R dash. Someone trying to say something? Okay, so this becomes RF by beta plus R dash. And if you have kept in your circuit, so all these R dashed, RF, these are in our hands, so we can select these things in this manner. What is R dashed? R dashed is RC plus RE. What is RF? RF is the feedback resistance. So if R dashed is much greater than RF, then of course RF by beta is even lesser than R dashed. because beta is around 50, 100, 150 like that, depends on the manufacturer. Then you can neglect this side, then it is approximately equal to V dashed by R dashed, and this approximation makes the IC independent of beta, and hence VC is also independent of beta. So your Q point becomes very stable. Again you achieve a stable Q point in the collector feedback. So this is the collector feedback, also known as the voltage feedback configuration. Then the emitter follower configuration. So in this emitter follower configuration, first time you will see the voltage source VEE. So yesterday someone was asking why we are not using VEE. Sometimes we do use the VEE, as you can see here, but this VEE almost appears to be the this does not this actually triggers the input base current only. This VEE is triggering the input base current only. So it was as good as if you keep VBB here instead of VEE here. Okay, so both are fine. So but you don't use both VBB and VEE because that is waste of resources. Now you see here how to solve this circuit. So this is just a circuit, you will see it as a circuit simply. Here this is the input loop, this is the DC equivalent by removing the capacitances, and this is the input loop that you are getting. Some IB current will flow, some IE current will flow in this branch. So if you get the KVL, you will find that this is minus IBRB minus VBE minus IERE plus VE equal to 0. And from this one we use this relationship between IE and IB, and we find out what is IB. We solve for IB. IB is again this, and you can see that here again you have the reflected input resistance. So in place of VBB, here it is VE, that's all, and this VE could have been connected in this side. Now the VC in this output side, so you see this output loop here, you have the VCE, so minus VCE minus, I hope you remember that VCE is like this. So minus VCE minus IERE plus VE equals to 0. Okay. So again you get this VCE equals to this. So instead of the VCC, we have a VEE here. So previously VCC was driving both the collector side and the base side. Now a VEE is driving both the base and the collector. Okay. So this is the emitter follower configuration. And in IC saturation, we have to put VC equals to 0, and it is simply VE by RE. That's all. IC saturation, why it is IC? It is actually IE, but IE is almost equal to IC. That's why it is a saturation current. Now the last one, common base configuration, it is same as the emitter bias. Even if you look here, you will see the operation is quite similar, but there is some different arrangement. So here both VE and VCC are used. There is a biasing voltage at the emitter side, also a biasing voltage at the collector side, no biasing voltage in the base, at the base, but these are producing whatever current that to be produced here. So you see the input side, the input loop you separate out first. So you have this VEE minus VEE plus IRE plus VBE equal to 0. This is IE. You please note the transistor. So wherever there is the arrow, that is the emitter side. Please remember that. The arrow is the emitter side. The other side is the collector, and this is the base side, where this plate is there, this rectangular plate is there, that is the base side. So you get this now. and now you have this I. You can solve for the IE. You can solve for the IE. There is no IB coming into picture because the IB does not suffer any drop. It does not suffer any voltage drop. There is an IB here, but it does not come in the KVL because it does not pass through any resistance. So only the voltages we have calculated in the KVL, and from there we can calculate the IE. Now you see the output side. This is the total loop. For getting the VCE, this is the VCE. VCE, this is plus, this is minus. So for this, for calculating the VCE, we have to get this IE, here the IC. So we are directly able to calculate IE, IC. IC is basically almost equal to IE. So IB does not come in picture. IB does not come in picture. So that's why this circuit is also a very stable one. The Q point is very stable. Now find out VCE. Use this entire loop. So VEE. So in this way we are going minus VE minus IERE plus VCE plus ICRC minus VCC equals to 0. Then VCE we can calculate because by taking IE almost equal to IC, we are able to find out this equation. And IE we have already solved, so this is the IE. This loop we can also solve and find out what is the collector to base voltage. Sometimes you may be asked to find this out also. This loop we can solve. So here we can solve this. So VCB you can solve. VCC is nothing but VCB minus ICRC. That's all. What is IC saturation? VC equals to 0. So I am taking IE almost equal to IC. This is VEE plus VCC by RC plus RE. This would be RE. Should be RE. So this covers all the different configurations which are given in the book. But please remember, the book also has a section named miscellaneous configurations. In miscellaneous configurations, there are no specific configurations given to you or shown to solve, but it means that there can be any sort of configuration in which any sort of network in which the transistor can be kept as an element, and then you have to solve it. And as we have gone through all these different configurations, I hope this confidence has gone into you that you can very well solve any such configurations, because what we are doing is nothing but using KVL and KCL. That's all we are doing. KVL, KCL, Ohm's law. That's all. These three very important tools, very important laws. These are laws, and we are using these as tools for solving our circuits. Along with it, some relationships which govern the transistor operation, which are the current gains. The beta, that IC is beta times IB, then that alpha, I think that IC is alpha times IE, and then IE is gamma times or beta plus 1 times IB. These relationships we are using. So it is not very complex. So any circuit that you may be given, you should be able to solve it. But these are some very interesting and very well known and very much used circuit, very popularly used circuits, popularly used configurations. So they are given in the book, and they have very specific names also. So that's why. So I hope this This actually completes the various DC biasing configurations. Next, there are also some more DC analysis we will keep on doing. After that, we will go into AC analysis. What more DC analysis could be there? In these circuits, whatever we have seen so far, we have only seen, okay, I will stop the sharing. Before that, if there is any doubt in any of these configurations, please ask me. I can go through that once more. We have around 10 minutes with us.
Excuse me, sir.
Yeah, Ashwin.
Sir, could you just share the screen of that last page?
Which one? Which configuration?
Yes, sir. Yes, sir. This one only.
Yeah, it
Sir,
was
here
shared, I think. Oh no, yeah.
IERE should be positive, na? In the second KVL equation.
In the second KVL, this one.
Yes, sir.
This one, we are taking V, then IERE. Yes. Sorry. Yeah, IERE should be positive, and this is fine. This is fine. Yeah, there it was my mistake, so I wrote it as negative. Thank you for pointing that out. And any question on any understanding level problem for anyone not able to understand how we are going ahead with the solution of the circuits? So some wisdom you have to apply. You have to look into the circuit first. Any random circuit, if you are given, you have to look into the circuit and formulate a strategy to go ahead. Normally the strategy will involve finding out solving the input loop. So in the input loop, sometimes we find out IB, sometimes we find out IE directly. Then it gives us IC, and then we solve the output loop. So normally this is a procedure, stepwise strategy, if you may say. This is how we are going ahead. Now, what further sorts of DC analysis could be done? So in all these circuits, we have seen only a single transistor. What if there are multiple transistors in the circuit? Then what happens? Then there will be another set of analysis, will be a bit more complicated. But at the end of the day, everything is KVL, KCL and Ohm's law. Please remember that. At the end of the day, everything is KVL, KCL and Ohm's law. We are doing nothing very special. We are not inventing anything. We are only using what we know. That's all. And trusting that knowledge. Okay. You can know many things, but if you don't trust that and don't use that, then it is your problem. Sometimes it happens to many of us. Even it happened to me also at some point in my life when I was a student. So I knew about that left hand rule was there, na? Fleming's left hand rule. So in one of the examinations, I didn't trust it suddenly. Okay, and I did a calculation and gave me a wrong result, so that some marks was deducted because of that. Suddenly I lost trust in that rule out of no reason. Okay, so this type of things should not happen to you. So whatever knowledge you are having, please have full trust and full confidence in that, and apply that also at the required at the time when it is required, when you have to apply that. Because you are new in this subject, that's why I am saying this, because after a while it doesn't even become a question of trusting these laws. This becomes a truth for you. So you always know that these are you can apply them all the time. Okay. For many of you this already might have happened, but for some of you, you may be still not very comfortable in using these laws, solving the loop, solving the node. So these things you have to become more comfortable. That's all. Then everything will be very easy in electrical engineering. Okay, so this ends with the lecture. So I will stop sharing the screen. and I hope everything is fine with what I am trying to explain to you. I am getting across to you guys. If there is any problem, anything you need, any feedback you want to give, please don't hesitate and get across to me through Teams channel, and I will be happy to address your concerns. So thank you, and goodbye for now.